Welcome to this video on building quadratic functions to describe situations, the beginning of chapter 4, which is quadratics. Today, in this first part, students will be able to measure falling objects using quadratic functions and expressions, and also talk about objects shot into the air as well. One important vocab word is the idea of what a quadratic function is. So we're taking a quadratic expression where you might have x squared involved, and having that be giving us an output in terms of a situation. We're looking at a table here, so I want you to take a second to think about what you might notice or wonder about this table and what might be important to look at. Something we can start with in this case would be looking at how much our x values are changing or how much our inputs are changing compared to how much our outputs are changing. So from 0 to 1, 1 to 2, all the way down the line, all of these x values are just going up by 1, adding 1 each time. So that's a constant rate of change. If we compare that to what is happening on the bottom, well, 0 to 16, that would be plus 16. But 16 to 64 would be a change of 48. And then 64 to 144 would be a change of 80. And this amount, as you might guess, is going to continue to increase as we go through this table. Now, if we wanted to look at how much these are changing by, so if I looked at the difference between 16 and 48, for instance, from 16 to 48, that's a difference of 32. And then from 48 to 80, that is also a distance of 32. These blue numbers are what's known as second differences, and when they are equal, you might remember from Math 1 that means that your relationship is going to be a quadratic relationship in your table. So in this first example, we have, if you look over to the right-hand side, we have a rock being dropped off the top of a 500-foot tall building. And you can see that after 0 seconds, it fell 0 feet, and then how far it fell after 1 foot, 2 feet, 3 feet, 4 feet, 4 seconds, 5 seconds. And you can see how long they've been falling for. So if we compare that, and that's kind of some similar numbers in the table we just looked at. So now if we want to start answering some of these questions, number 1 asks, how far will the rock have fallen after 6 seconds? If we look at what happened in the data we have in front of us, from 4 seconds to 5 seconds, that difference is 144 feet. It fell in 1 second. From 144 to 256, that difference is 112 feet. So just based on those two numbers, we can tell that the rock is speeding up, and each second it's falling further and further down. So our hypothesis here would be that in 6 seconds, it would fall more than 144 feet. So that means it would hit the ground at 500 feet down, it would hit the ground before 6 seconds has elapsed. So it would basically, you could say that it would fall 500 feet because 500 feet would just be the ground. Now, if I look at some of the data we had from before, we had each of these first 5 data points, which we can see next to our building, are multiples of 16. We do 16 times 1, 16 times 4, 16 times 9, etc., etc. Then this person, Jada, noticed that 1, 4, 9, and 16, those numbers here, are the same thing as 1 squared through 5 squared. So for part A, use Jada's observations to predict the distance fallen after 7 seconds. We'd be able to say that we could just do 16 times 7 squared seconds and put that into our calculator, 16 times 7 squared, and we would see that the answer is 784 feet. And that would be your answer for part A. So for part B, if we are thinking about our table from before, we basically want to look, well, where can I get like our input of 1 through 5 seconds and then our output. So if we look at some of these, we're basically doing 16 times 1, 16 times, or 1 squared, 16 times 2 squared, 16 times 3 squared, and that would keep going like that. So if I wanted to know the distance after t seconds, we'll say, so distance would be equal to 16 times the number of seconds, t, squared. Or if you wanted to write it with y's and x's, you could say that the equation here for how far it would have gone is 16 times x squared, if x is the number of seconds and y is feet. And we could check our answer pretty easily by doing 16 times, with 2 seconds, it would be 16 times 2 squared. Well, we already know the answer is 64, so that means we found our equation correctly. In our next part of this section, we are thinking about a famous Italian scientist named Galileo Galilei, and he worked with other medieval scholars to study the free falling motion of objects. In our last slide, we said that distance can be given by doing d for distance times 16 times the time squared. So if I wanted to know how far it fell, how far it went after half a second, I'm basically going to just put in a 0.5 into my equation and do 16 times 0.5 squared. And I can just type that directly into my calculator. And that would give me an answer of only 4 feet. And so we now look further down our page here, and we have 2 different people looking at this situation in different ways. So if I look and compare the 2 tables down here for objects fallen, on the left-hand side, they're the same, because they both start at 0 seconds and go through to 4 seconds, eventually getting to t seconds. And so I want to think about how I'd fill out the rest of these tables. And so we will do that now. If we want to fill out our first table, we are looking at the distance fallen. We already know the equation we're going to use, so we really can just fill out our table by doing 16 times the number of seconds squared. So I could do 16 times 3 squared and get 144 right here, 144. And then I can do 16 times 4 squared and get 256. And so we know that here, distance equals 16 times t squared is this equation for our final row. The table on the right is different because this is talking about distance from the ground still remaining. If our table on the left is how much distance you've gone, we can just subtract that from the initial height of 576. For instance, if we did 576 minus our equation with a 1 in it, 16 times 1 squared, that equals 560. And so that gives us our next row, so that we could do 576 minus 16 times 2 squared for this. So I'll write that down here. 576 minus 16 times 2 squared, and that equals 512. And so we can just fill out the rest of that table by doing 576 minus 16 times 3 squared, and that equals 432 right here. And then we do our final one would be 576 minus 16 times 4 squared, and that equals 320. And that means that 576 minus 16t squared, and you can use an x r a t if you wanted, and then that equals d for distance. So they're really just starting at different points. One is starting at the top, one is starting at the bottom. And so we're going to now look into Desmos graphing to see where we can look at comparing the graphs with their equations and tables all together. We are now looking at Desmos graphing using their graphing calculator application. And I took the first table and second table and filled them in here on Desmos. And we can look at the red graph is basically telling us the time that's elapsed and how far the distance has gone, like how far the ball has gone. So you can see those amounts, 16 up to 256. And if I look at my second graph in purple, that is telling you if you're starting out at 0 seconds at the top of this 576-foot distance, you can see that it's falling at a very similar rate. And you can see how one purple graph is kind of following with the path of the ball, and the red graph is telling you how far the ball has gone as time elapsed. And you see they're kind of reflections of each other. This applet is a good demonstration of what we're talking about right now, because you can see that we're starting out with the ball 0 seconds in, 576 feet up in the air. If I click start, you can see that as 1 and 2 seconds elapses, you can see that the ball is increasing in its velocity and its speed and falling down faster and faster. And we can see that it's kind of curving as time goes on and going more distance up and down as you're going further to the right. To end part 1, we have an expression of 16t squared. We've seen that a few times this section, or this part 1 so far, after t seconds, and they're dropped from a height of 906 feet. So we want to figure out what is the height in feet of the objects 2 seconds after it has dropped. So we're basically trying to figure out first, like, how far is it going if you've gone for 2 seconds. So we can find that answer pretty easily by doing 16 times 2 seconds squared. So that would equal to 64 feet, like so. So if I know that I've gone 64 feet, I would just need to take away 64 feet from 906. And that subtraction would give us an answer of 842 feet. And that would be the answer for part 1 of this closing problem. It went 64 feet, and it dropped 64 feet out of that 906. So basically, if I wanted to know the distance for the height of the object to give me 842, I know I would have to start out with 906, and it's going down by 16t squared. You'll notice that sometimes our 16t squared that we've seen a lot in this chapter is negative. That's usually when you're talking about like the height at which it's going to as you're going downwards from 906. It was positive when we were just talking about the total distance it went, like we started with at the very beginning of part 1. And this idea of applying quadratics to free-falling objects is very common. The thing to remember is that we've simplified this a little bit to get 16t squared to represent the distance an object falls. There's a lot more goes into it when we talk about things like air resistance and things like the size of the object and mass of it might make an effect as well. And that's something that you'll cover in future lessons in classes.